So here we are going to continue what we left off for the 102. And for 102, we only mentioned what is the meaning of a linear combination and what is the meaning of span S. And in the previous example, we just saw that some of the set, for example, this set, if you have a plan in R3, then it is a span. It is the span of these two vectors. And if you only have one vector and you do the span, it is the straight line. But somehow, say for example, if you choose the set to be the unit ball, the ball in R3, then it doesn't look like it is a span, because if you have any vector, then every point on the straight line should be included in this set, right? So ball is not span S. Right? So in a space, some set can be written as span S and some set cannot. And we will explore some more details about this property. Okay, so this phrase is very common in mathematics. The following are equivalent. So it says that I'm going to write two statements or several statements, and they are the same. Okay? So the first statement says that a set is equal to span S for some S. So just try to use some of the example on the left-hand side. V is equal to the plan, and S is equal to the two vectors. The second description is quite different. Okay, V is again a set, but V satisfies the following. The first one, V is not going to be empty, because you can always choose 0, 0 as the coefficient. So zero vector is always in a span. The second property is saying that if I find a vector in V, for example this one, I find a vector in V and I have a scalar k in the real number. So suppose I have these two things, then k times V is also in the set. And this is basically what we draw here. If you have a vector in V, and this V can stretch to the infinity, any scalar multiple of this vector is also in V, because it is the span. Okay? So if you want it to be a span of S, then this vector should stretch to infinity. So I have a vector, a scalar, then the scalar of this vector is also inside this set. And the third one, if we have two vectors in V, okay, then its linear combination should also in V, right? So then U plus V, this is one of its linear combination, should be also in V. And such a property is quite common in many branches of mathematics. For example, if you think of real numbers, if you take two real numbers, a times b, it is still a real number. If you have two real numbers, a plus b, it is still in the real number. And in this case, we say it is closed, just 封闭, okay? It means that it is inside there. If v is inside, k is a scalar, then kv is also inside. So we say it is closed under scalar multiplication. Under means with respect to this operation. 在中文不会讲，存量乘法，在存量乘法下封闭。Okay? And the second case is the same, closed under addition. Okay, so addition is you try to add u and v. So it is closed under u and v, under addition. So if you look at some of the set on the left-hand side, some of them is closed, some of them is not. And let me give you some more examples. Can I change the page now? Oops. Okay, so it looks like I'm a bit fast. I will try to adjust my pace next time. Okay, so I think giving you some example will help you to understand what's going on here. Okay, so first example, we have to have an S. It will be easier to start with S. Okay. So I want to emphasize S is a set. Okay. So it has braces outside. By the way, let me put it under here. This one is called a brace. And you know why it's called brace? Because it looks like a brace. Like this. Okay? So it's called a brace. It's not called a big parenthesis. Okay? This is parenthesis. Like a parent. Parenthesis. Okay? This is the hardest word. And then the second one is called the bracket. Okay? Bracket is just like a 篮子. Okay? So it is more squared. Someone called it squared parenthesis. But rarely people call that big parenthesis. It's only in Chinese we call small parenthesis, middle parenthesis, and big parenthesis. Okay. But anyway, a set need to be put into a parenthesis, put into a pair of braces. And inside the braces, you will have some vectors. And vectors are enclosed by these notation. So if we have S equal to just one vector, the span S is equal to a straight line. Okay? Any multiple of S will be included. Any linear combination. And it can also be written as V is equal to xy, such that x is equal to y. This is the formula that you know in high school. But then, if you consider the set xy, x squared plus y squared is equal to 1. This is a set, looks like this. It is a unique circle. Okay, and if you look at this set and you are thinking if this set can be written as span S or not, then you might wonder, okay, maybe I will choose this one as the S. But then if I choose this one as S, then the whole straight line should be included, right? This is a violation to the linear combination. So this set is not span S. No matter whatever the S you choose. On the other hand, you can try a different set. For example, you choose xy and say xy, their product is equal to 0. So in this case, either x equal to 0 or y equal to 0. So the set is just like the cross. And now you might wonder again, can I pick some vectors on here so that the whole set is span S? I can pick one vector here, and then I pick one vector here. But then its linear combination is outside. It is a trouble. So this kind of set is not a span. So the two statements in the previous page help us to recognize some set as span S and some set is not. If you see the set is very flat, it stretches out to the infinity, either a point, a line, or a plane, then it is span S. But if it is not closed under some scalar multiplication or not closed under addition, then it is not span S. Because no matter what S you choose, it will violate the linear combination, the definition of a span. And the reason we are talking about this is the span S is very common in linear algebra. If you think of a lot of cases, for example, if you have a set of linear equations, okay, in high school, you have x, y, z. You have a set of linear equations. And what is the solution set? The solution is either a point, a straight line, or a plane, right? And so in the end, we are going to tell you that the solution set is always look like this. And also, in some future topics like machine learning, you will have some vectors, and these vectors we call that as the feature vector, meaning that these are the important things, and we want to project all those things onto the space, onto the span of these vectors. So the span is one of the biggest concepts in linear geometry. So let me show you that actually you have seen this before. Okay. So forget about the title first. I believe you have seen an equation like this. For example, x plus, say, 1x plus 2y plus 3z is equal to 0. 4x plus 5y plus 6z is equal to 0. Okay, So such a thing is called linear equations, and the combination of them is called a system of linear equations. But there is a weird word at the beginning. It's called homogeneous. And homogeneous has a lot of different meanings. At least here, it just means, well, let's not write the Chinese first. In here, it's just a mathematical definition. It says that on the right-hand side, everything is 0. If a system of a linear equation, all the coefficients on the right-hand side is 0, then we call that as homogeneous. It's just a name. It's just a name. And the literal meaning means 对齐的. Okay, so it kind of tell you that it looks better than arbitrary numbers here. Okay, but in mathematics, homogeneous has all different meanings. Okay, and we have seen this before. We know we can write it as matrix and give some vector of variables and saying that it is actually equal to 0, 0, 0. So every linear equations can be written as A times a vector equal to the other vector. And if the right-hand side is a 0 vector, then we call that as homogeneous. Okay, should be easy enough. Just a term. The right-hand side is 0, then it is homogeneous. Now, let's define the kernel of the matrix A is written as kernel of A, okay, and it contains all the sets of V such that A times V is equal to 0. So basically, it is the set of all homogeneous solutions. Now, if you think of this, say in the high school, right? Maybe you will start solving this, and you will do some elimination. You will realize that this one has more than one solution. It actually has a lot of solution, and you can try to solve that. But in the end, the solution looks like a straight line. I did not do the calculation, so I don't know which one it is. But it is a straight line in three-dimensional space. And I will tell you why later, maybe in the next class. But the point is that the kernel of A, if you look at the solution set of any homogeneous solution, then it is always a span S. And if a set can be written as span S, if a set V can be written as span S, then V is called a space.